Where we left off last class was I had started showing you how we're going to build a contingency table in Excel. So we'll kind of work through that example today. Got this recording, so you can kind of have that to go back to up on that YouTube playlist. So very helpful for the next Excel assignment, which I'll get posted up after classes, after I've done teaching classes today at about 1 o'clock. Sorry. So where we left off was we had this data and I kind of saved it where we left off, and it just had the county names, had our median household income, and it had the percent of that county that was vaccinated. So this was back, I think, last fall. So there was more variation in like kind of the percent of counties that are vaccinated. So it might be a little interesting to kind of look at this relationship. Okay. And then once we build this contingency table, I'll kind of talk about, we could actually use that multiplication rule, find some of these conditional probabilities, intersections, unions, all these different things. So where are we going to start out so we can see everything? Okay. So for this very first one, what we're going to do is we're going to count the number of counties here that have above the average income, and then also above the average percent of their county, of their population vaccinated. Right? So once we have the number of counties, right? I think I alluded to this last class, but how can I turn that maybe into a probability? Well, let's say 1,000 of the counties meet this criteria out of 3,100. Just divide by the total number of counties we have, or the total number of observations. Okay. So what can we use to count the number of observations if things are true? We're going to use that count ifs formula again. Okay. So this is why I want you to kind of use that for that first Excel assignment, building that histogram without just using that built-in tool, because we're going to use this count ifs formula again. So we'll start it. It's going to be a little bit different than what we did before. So the first thing we're going to do is select this household income variable. So I'm going to hold Command Shift on a Mac, hit the down arrow, kind of a pain. Actually, I'm going to scroll back up so we can kind of see what I'm doing. Or you could just go up to the formula bar. That's always an option. It's just when I'm working through this, I know it's very small, so that's not how I do it. So you'll kind of notice it shows me it put that reference in there, comma, and I could type the criteria in here, so I don't have to like do all this scrolling. I'm just doing that because I know it's a little bit easier to see up here if I don't just use that formula bar. Okay. So I've got that range of data in there, right? And then we're going to put a comma. The second thing is, well, I'm looking through that household income variable and I'm only counting it if income is greater than the average, right? Or above average income. So I'm going to put a greater than sign here, right? Also, was that my computer? Yes. Make sure I turn the volume off there. So greater than, and then we'll use an and sign, right? Because I'm going to use a cell reference. Now, I could type in this average, I guess, if I wanted to, but I want to show you that, maybe after this, I'm not just interested in being above the average, maybe above like, the 75th percentile or some other value, right? Maybe $60,000, whatever income I'm interested in. So we're going to use this cell reference where we had that average calculated. Okay. Any questions up to this point? We're okay with this so far? So then we'll put another comma. So we want to count the county if it has above average income. And of course, now I can't see my labels here, but the other one was above the average vaccination percentage. So I'm going to go over here and I could select this column of data that has the percent vaccinated values, or because I don't like to scroll a whole lot, I know that it goes from cell 2 to 3,142. So I can just type this in, but I know that instead of column C, it's in column D. So I'm just going to type it in, but you could select it if you find that, that's easier for you. Like I said, I just hate scrolling up and down. So since I can see that reference range there, I can just type that in. Okay. And then when I look through this percent vaccinated variable, well, what do I want to count? Well, I only want to count it if it's greater than the average percent of a county that's vaccinated. Okay. So select the first variable you want to look through, then put the, what you're checking to see that variable kind of criteria is, then select the other variable, and then the criteria that you want to make sure is true for that. variable. Okay. Any questions here before we keep going? I'm getting some looks. I don't know if it's like bored looks or if it's like where I'm lost looks. So, or everybody, any questions before we keep going here? All right. So I've got 932 of the counties fit that criteria. Okay. So I'll show you what I think is a quick way to do this, right? Because I know that I'm really going to be using a pretty similar count ifs formula when I want to get the frequency of these other categories. The only thing that's going to change is instead of being greater than the average, maybe sometimes I want it to be less than or equal to the average, but my range of data stays the same. So I think an easy way to do this, you can freeze the cells and like copy it over and then go and change them. But really all these cell references should stay the same. So what I could do is freeze everything. So I'll show you two ways of doing this. I could freeze everything. So let's go ahead and do that. Now, if I try to select all of this and freeze it, it doesn't do anything because there's like greater than and less than signs in there. So unfortunately, I've kind of got to select this in parts here because it doesn't like those greater than signs. And I'm just kind of using that F4 or Command T shortcut to throw those dollar signs in there very quickly. Okay. Any help with that or good with that? So now hopefully, if I froze everything, when I copy this over, what number should I see? Yeah, nothing should change, right? The same number. So I'm going to copy that over and then copy it down. Okay. This is just so I don't have to type in that count ifs formula again. And then going to go in here and say, well, look, and actually, I now know, I'm going to move these up. I don't know why it does that. So I can kind of see what my headings are here. I now know that in this category, I only want to count the counties if they have above average income. So if that variable in column C, which was income, okay, is that greater than the average? But now I only want to count it if it has the average vaccination percentage or less or below that. Right? So instead of being greater than the average vaccination percentage, I want less than or equal to. Right? That's all I have to change, right? The data is still in the same place. The values that I'm kind of using, right? The averages there, those are in the same place. So all I have to do is go in and change those signs. Okay. Then I go over here. What's this one want? Well, this is average income or below. So less than or equal to the average income, but above the vaccination percent, average vaccination. So I don't have to change that one, right? So just go in and change that one less than or greater than sign to less than or equal to. And then this final one, this is, I wanted them both to be either the average or below, or it's just another way of saying less than or equal to, less than or equal to. Okay. So I think that's an easy way to have to only type in that count ifs formula once, freeze everything, copy it over and down, and then just go in and make sure that your equality signs are kind of matching up with the events you're interested in, right? In this case, we were just doing above the average and then, or above the mean, and then less than or equal to the mean. So if that makes more sense, you could even change your titles. Instead of doing average vaccination or below, you could say less than or equal to the average, right? That kind of makes it easier. You could change that heading. Okay. Any questions here before we keep moving? All right with this. Okay. So I've got these frequencies now. What's one thing I left off here? Well, I have my totals. I have those total columns. Okay. So how could I, what did we say? How could I reproduce those totals if these were probabilities? Do you remember what I said? We could add. So if I want the number of counties that have above, right, the total here should be the number of counties that have the above average income. Instead of typing in like a count if or a count ifs formula, well, I know the number of counties that have above average income and above average vaccination percentage. There's 932 of those. And then the number of counties that have above average income and have less than the average or less. I should include the equality there, but I'm just speaking a little lazy. Is 395. Well, that would cover every single possible county that has above average income, right? So I said to reproduce these totals, I could just add across the rows, right? Because I know if I take number of counties that have above average income and above average vaccination percentage and above average income, or that average or below, that's every single county that has above average income. So that would reproduce my totals. Okay? Now, one thing that's nice is if I use that sum function, now when I drag this down, right, I want to just keep adding across the rows. So now this one updated that cell reference. So that's pretty nice. And then to reproduce these, I said I could add down the columns, right? Similar sort of idea. If I take every county that had above the average vaccination percent and above average income, and then I add to that the number of counties that had above average vaccination percentages or below the average. Well, that's every county like that had above the average vaccination percentage, right? And it's kind of because we created these events as being A complement, B, and B complement. We didn't do that, then all bets are off. But that's how we should be building these contingency or these joint probability tables. Okay. And I should probably move this so you can see what I'm doing there. Right. So I just took the sum of kind of these two. I can then drag this or copy this across. My cell references update. So I'm now looking at the sum of these two cells as well. Now, it doesn't matter which way I do this, but let's just say I add these two values up. So you can't see this now, but this is the number of counties that have the average income or below, and the number of counties that have above average income. What should these add up to? Yeah, it should be every single observation, every single county, or my sample size, right? The total number of observations in this data. So hopefully when I hit enter here, I get that 3,141. And a good way to check yourself here, now we already have this from last classes, just using that count function that lets you know, okay, hopefully if I've got all my count this and my sum function's working correctly, I should be getting that same value here. It's a good way to check to make sure I didn't make any mistakes. You know, often this might be something like, and I don't think it'll occur in this data set, but like, let's say, I don't know, it didn't work there. Let's say I forgot to like include my equalities. Okay, so this one doesn't change anything, but if we had some other values, like it might be missing a couple observations if I forgot my equalities, right? In this specific data set, even if I made that error, I guess I lucked out, right? But in things that are dealing more with like integers, it's a lot more likely that if you don't include those equalities, you'll be missing some observations, okay? All right, any questions up to this point? I'm just going to drag this down here now so it looks like a better table. Okay with this? All right, so I've got, this table now. Well, the problem is I need probabilities, right? So I can do this in two steps, right? So we would kind of call this is like my joint, or sorry, you kind of think about this might be my contingency table, but it's in terms of frequencies. I want to turn it into a joint probability table, right? I want the probability. So the way I do this, just to make it easy, so I can copy this, I copy, and I did my shortcut there. You could right click. I guess I do Control C. I'm guessing on a Mac, it's Command C, right? And then Command V or Control V to paste it, right? Now, I don't want these frequencies here, so I'm just going to delete those, but at least I've kept my labels. It was a nice, easy way. I didn't have to type all this out over again. Right? So now I want my table to not have the frequencies, but I want probability. So what am I going to do here? Yeah, divide each number by the total. Now, instead of typing, so I could go up here and say, okay, take the frequency for this category, right? And then divide it by my total number of observations, which is over here, right? And I want to do this instead of typing my numbers in, because then if I ever go back and change things, we'll see everything will update. If I didn't, I'd have to go back in every single place and type 3,141. It's going to, take a lot of time. Now, the problem is I might think, okay, this was taking G6 divided by I8. If I copy this over, oh yeah, that's good, because then G6 will become H6, but I8 would become J8, right? So if I simply copy this over thinking everything's going to work out okay, I start getting errors, right? Oh, because I can't divide by no number, right? It doesn't work. So what do I need to do? Yeah, I want to freeze that cell reference. Oops, and not erase it. Of wherever that total number of observations is. Okay. So once I have that, now when I copy it over and then copy it down, notice it's lining up with that original frequency table and just dividing everything for that total number of observations. Yeah.
How do you make it so you only do something decimal points over?
So like you don't want to see like 8 of them. So just visually what you can do. Now this doesn't change the number that's stored in the cell. In fact, this is actually, these might go out to even higher number of decimals, but if you go up to this home tab, there you should have, there's like a number, there's these different categories. Under the number, there's these little zeros with an arrow. And I always, honestly, it helps me to hover and then look at it, because if I want to increase or decrease the decimal, I don't know why, but for me, I always mix them up. Like it always makes me think, when I see the right arrow, I think, well, that should be that I want to see more, but it actually means that you're going to see less. So usually I get this like wrong on the first try. I got it here because I hovered over. Oh, wait, I don't want more decimals. I want fewer, right? And then you just kind of play around with, however many decimals you want. But yeah, these little kind of zeros with the arrows. And if you hover, it tells you, do you want to decrease the decimals that you see or increase, right? But notice it's not actually, if I were to use these cells and like reference them now, it's not using 0.297. It's actually using whatever the value is out to, I forget the number of decimals that Excel stops at. It's a lot. But yeah, if you want to make it visually kind of a little bit cleaner, you could do something like that. Any other questions before we keep moving here? We'll cover this. Okay. So now I've got my contingency table. I could start to ask, I guess, some somewhat interesting questions. So what's the probability that somebody has above average income? Well, that's just, you go to the event you're interested in, you go over to the total column. That's pretty easy. Okay. Well, what if I wanted the probability of having above average income and average vaccination percentage or below? Right. And this is where my labels I probably should have thought about. I probably should be abbreviating things so that we don't have, so I'm going to do average here just to make it a little bit fewer words. Okay. Well, that's just those top 4 left cells represent intersections. So I want above average income and the average vaccination percentage or below. So that would just be this cell right here. I could also find a conditional probability. So I'll do this one. So I've got a conditional probability here. So if we kind of remind ourselves, anytime we wanted a conditional probability, we said, well, whatever I'm conditioning on, that's kind of now making my experimental outcome space no longer 1, but something smaller. So I'm going to have a different denominator. What's that denominator? Well, it's just how much of this experimental outcome space of 1 is left in whatever I'm conditioning on, right? Because I know that I'm somewhere in event B now. So we'll kind of divide by whatever we're conditioning on, the probability of whatever we're conditioning on. And now the only way that we're going to see A occur is if we're somewhere in where A and B overlapped. Because we know that we're somewhere in B. So the only way that we're now also in event A is if we're somewhere in the intersection of those 2 events. So for us, that's going to be what? The probability of having above average income and above the average vaccination percent. So where would that be? Right here. I would then divide that by what? So what am I conditioning on here? The total number of above average vaccinations. Yeah, right. I'm conditioning on that it has above average vaccination percentage. So I divide by the probability of whatever I'm conditioning on. Well, how do I get that from my table? Well, that's just go to above average vaccination percentage and go down to the total, right? That kind of represents the probability just of those events themselves, the total columns and rows. Okay. So found that. Okay. So just looking at this, so these are just questions we've looked at with other contingency tables. Now we're just doing it in Excel, right? And it's as easy as clicking on these cells, right? I don't even have to type the numbers out. I don't have to worry about the decimals, right? You know, I can just click on that cell. Are these events mutually exclusive? Do you remember what mutually exclusive meant? So visually, if I had like a Venn diagram, what did mutually exclusive look like?
Isn't it what's, if you have -1?
So that's the complement. We kind of think about the event and its complement add up to 1. The next thing we said when we were talking about mutually exclusive, that was like, I have 2 circles that don't overlap. So we said events are mutually exclusive if the intersection, the probability of the intersection is equal to, they don't overlap here. What's the probability I'm in both these events? 0, right? So if they're mutually exclusive, the probability of the intersection being in both of them, well, it doesn't exist, so that probability is 0. Well, I don't have any zeros up here, right? So pretty easy to check to see if events are mutually exclusive, right? Because I've got my intersection of these events, non-zero, they must not be mutually exclusive. The only way they'd be mutually exclusive is if I see a 0 up there, which wouldn't be a very interesting example, right? Are these events independent? So if we remember what we said for independence, so what we said for independence was that this conditional probability had to be the same as the unconditional probability of that event. Okay. So here, if I've got the probability of being above the average income, that's my event A, 0.42. Well, I found the probability of having above average income conditioned on this other event, right? Having above the average vaccination percentage, that's 0.55. Those are not the same. So if they're not the same, we would say they're, I guess, not independent, or another way of saying that is they're dependent, right? The one event depends on the other here. So it's really kind of alluding to the fact that, look, if I put a county at random, the probability, actually, let me do this the other way around. Let's do another example because I think it's a little bit more interesting and maybe makes more sense. So let's say I did above average vaccination percentage. Well, that would just be above average vaccination percentage, go to the total column here. And then I'm going to do what's the probability of having above the average vaccination percentage given I have above average income, right? So I'm just kind of switching my event A and B here. So really what I'm checking to see, and I should already know the answer to this, right? So now I'm just saying, does the unconditional and conditional probability of event B, does that equality hold? Well, I should, before I even try to calculate this, I should know that these aren't equal, because if A and B are independent, B and A are independent, right? So I should know that I'm not going to see 0.536 when I calculate this, but just to make sure, right, what's the probability I have above the average vaccination percentage and above average income? That's right here. I'm then going to divide that by, well, now what event am I conditioning on? Now I'm conditioning on, do I have above the average income? So I go here. Okay, now I'm dividing by the probability that they have above average income. Right? So this one makes a little bit more sense. And the reason why I flipped it, you'll kind of understand, I think, hopefully after I if I just selected a county at random, the probability that they have above the average vaccination percentage, pretty close to 0.5. That makes sense. So there's probably not a lot of skew to this data. Okay. If it had no skew, what would this probability be? So let's think about, we were using the mean as our cutoff. Right. So here we're getting that about 53% of the data is actually above the mean. Right. If instead I saw that probability was exactly 0.5, I know that that would be a symmetric, like the data would be symmetric, right? Because then the mean would be the same as the median. Because I was using that mean as the cutoff, but if it made it such that there was 50% on either side, well, that's the median. If the median is equal to the mean, we say it's symmetric. If it's not, we've got a little bit of skew. So we do have some skew to this data, but not a lot, right? We're pretty close to 0.5. You know, you can imagine like if I had a really skewed data set, like this could be something like 0.7, right? Or the mean is like really far away from the value that splits the data in half. Yeah.
Can you go over again, which cell would be 0 if it was mutually exclusive?
It depends on what events you're talking about, right? Now, in this instance, you know, if there was 0 counties that had above the average income and above average vaccination percentage, then we would say having above average income and above average vaccination percent would be mutually exclusive, right? Because I have 0 counties, there's no overlap there. So if I saw you, I mean, we would think about 2 events are mutually exclusive if their intersection is 0. So it would really depend on what 2 events we were wanting to know if they're mutually exclusive. I think what I had said was just above average income and above average vaccination percent to just kind of give an example. But you could check to see if having average income or below and average vaccination percentage or below were mutually exclusive by seeing if that intersection was 0 as well. Is that? Yeah. Any other questions before we keep going here? So I kind of want to make this point. So if I selected a county at random, the probability has above the average vaccination percentage is about 0.5. If I then give you this additional piece of information, which is, well, I've selected a county at random, you can't see it, but I can, and I'm going to tell you that it has above the average income. Right? So if a county has above average income, well, now the probability that that county also has a higher percent of their populace vaccinated goes up to 70%, right? So this is telling me that, you know, probably I think this kind of makes sense that poor communities were having either skepticism or difficulties getting access to the vaccine at this time, right? Or that there's some, you know, there's some kind of relationship between these 2 things. And that's a pretty big increase. I mean, almost 20%. I mean, 0.5 to 0.7. And so, you know, these start to become pretty interesting when we think about these conditional probabilities and put some actual events to them. Well, that's pretty interesting to know. That tells me, well, maybe I should look into why poor counties aren't, you know, or they don't have access to the vaccine. Is there something about mistrust of the government or something like that, right? But at least it tells me maybe I should look into this. Okay. Any questions over anything we did here in Excel? I thought this might be an interesting example. I didn't know this ahead of time, so this is interesting to me too, that it increases by that much. So it's a problem that I've used labels when I want to update this. I probably could have kept the labels a little more general, although it would have been harder to follow along. So maybe I wanted to just, you know, if I had my labels to be like above X, right? Or greater than X and then less than or equal to X, so that I could change the cutoff I was using, then I wouldn't have to go in and update my labels. But there's no, at least there's not a way that I want to use class time to show you how to kind of get those labels to update using cell references, although we could, you know, if I had up here created kind of my just the text, typed it in and then referenced, then I can go back in and change that. If I would have just kept it as X, then it just doesn't matter what I change my cutoff to. So that probably would have been better, but like I said, would have been harder to follow. But I can kind of show you that if I had just kept it as a general X value and not, you know, said the mean or the average, well, then if I go back in and say, okay, look, yeah, I guess, you know, having above the average income is interesting, but maybe I'm really interested in if a county has above average income, can they get not just above the average vaccination percentage, but can they get more than half of their population, right? So there, can they get 50% of their county, right? Does it change the probability they get 50% of their county vaccinated? Right? So now when I hit enter, since I use my cell references, all my frequencies should change. It's no longer going to be finding do they have above the average vaccination percentage. It'll be do they have above 50%, right? Which is why I said, you know, making the labels kind of more general probably would have been better, but harder to follow. But now when I hit enter, all my frequencies should update and all of my probabilities should update as well, right? But sure enough, I hit enter, everything's updated. And not only did that update, but because I was using cell references down here, and I'll hit Control Z so I can show you that. Here's my probabilities. Once I change this to 50. Oh, kind of quickly saw, but they changed as well. Right. But notice it's still like now the probability they have above 50% of their county vaccinated is 0.25. So there's only about a quarter of counties that actually got more than half their population vaccinated. But if you told me that that county had above average income, well, then there was like a 42% chance that they had more than half their county vaccinated. Right? So we're still seeing there's this definite relationship between average income in the county and kind of what percentage of the population they were getting vaccinated. Any other questions here? So basically your Excel assignment, the latter half of it we probably won't cover until next week. And then I know we won't, I shouldn't say probably, we won't cover until next week. But the bulk of the assignment is like what we just did here. So you'll start out with some data. I'm going to kind of give you two events and then their complements. You'll use that count ifs to calculate your frequencies, turn that into a joint probability table, right? Just by dividing by the number of observations. And then I'm going to have some questions like this. I'm going to ask you for the probability of certain events, their intersections, conditional probabilities. Are they independent events? There's actually one other thing I could ask you for that I didn't show you here, but to be fair, I'll do it. Okay. So let's say I wanted the probability of having the average income or below or above the average vaccination percentage. Right. So now I'm looking for the union of two events. Remember, how can we find the union of two events? So if I want the probability of A or B, how could I find that? Remember, so I could take the probability of each event and add them up, but I still need to do one more thing, which is what?
Subtract the intersection.
Yeah, subtract what I double counted, which would have been what's in both, or subtract the intersection of those two. So here, once again, in Excel, I don't have to worry about numbers. I can just click on the cells that these things are in. So what's the probability of having above average income? Right here. Add to that, what's the probability I have above the average vaccination? Actually, sorry, I read that event wrong, didn't I? It was average income or below, right? So what's the probability of having average income or below? Right here. Add to that the probability of having above the average vaccination percentage right here. And then subtract the intersection of these two events. So the probability they have average income or below and above average vaccination percentage was in that column right there. So I can kind of find unions pretty quickly, just clicking on these numbers. Once again, don't have to worry about the number of decimals I'm going out to. Don't have to worry about typing this in wrong. If I'm just clicking on the cell, as long as I've selected the right cell, everything should be good. Okay. Any questions before we kind of get out of Excel here? Let me double check on this, but I believe, and I'm second guessing myself now. Okay, I did update these yesterday. So I updated the skeleton slides yesterday. So if you downloaded them, I added in some new slides because I figured we'd have a little bit of extra time after we got through the Excel stuff to kind of start the next topic. Okay. So if you downloaded them, you'll have to go back to Canvas and then re-click on those skeleton slides. We got to, oh, where's my Excel stuff? So I'll kind of set up Bayes' theorem. I have kind of the review here. We were using some of these as we were working through the Excel, but I want to set up how we're going to use this thing called Bayes' equation. I might get through one example today. We'll definitely do more on Monday, but at least kind of introduce it here. So what we're going to be doing with Bayes' theorem, it kind of relies on this idea of conditional probability. So we might start out and we have this unconditional probability. We have what we call a prior. So we know the probability some event occurs is 0.2. We're then going to conduct an experiment about another type of an event. And once we see that outcome, we'll update whatever that prior was. So it's essentially like, given that I've now seen this outcome of this experiment, well, now what's the probability of this event that I was interested in? Okay. And I think this will make a little bit more sense in just a second. So we're going to start out with two states of nature. Okay, we'll call this S1 and S2. And they're basically going to be complements of each other. We could, if we wanted to, call this A and A complement. But just to make it easier, we'll think of these as states of nature, right? So this might be something like someone's either guilty or they're not guilty. They either have a disease or they don't. They're pregnant or they're not, right? Something where we've got, right, two different outcomes, two different states of nature. Like someone actually is either pregnant or they're not. You know? I don't know that just by looking at, well, I guess far enough along I might, but if I just look at someone, I don't know that, which is why there's pregnancy tests, right? Or I don't know if somebody has a disease or not unless I give them a test for that disease, okay? But they either have a disease or they don't, okay? So I said that these are kind of complements. So another way of saying that is these events are exhaustive, right? I have to either be in one of these states of nature or the other, right? So they must add up to one. So I take the probability that someone is, you know, pregnant plus the probability that they're not pregnant. Well, those are the only two outcomes, so those have to add up to one. Okay? We're then going to have some tests that we run. We'll call this E. I don't know why this is just like a general notation that they use when we're looking at Bayes' theorem, but I've got this E, right? This is going to be the outcome of this experiment that I ran, right? This experimental, you know, usually it's a test, but it could be, you know, think about instead of, you know, a test for a disease, right? We might have a jury, right? That's the experiment. We run this courtroom, you know, trial, and the jury kind of has their outcome. Right? So we've got E and E complement being the two outcomes of the test. Okay. We're going to, for now, assume that we have no inconclusive results on these tests. Okay. So we're saying one thing or the other. So I said rephrase from the last slide, but I kind of got rid of that slide. So let's think about, maybe I want to know the underlying probability of an event, given that I see some outcome of the test, right? So what's the probability I'm in whatever state of nature I'm interested in? What's the probability somebody has a disease, given that I saw the outcome of the test says that they were positive for that disease, right? Or I can kind of set this up as a disease, kind of using the first example I'll work through is kind of an HIV example. I actually grabbed these numbers from online, so this should be fairly accurate. So I want the probability, the state of nature is that someone actually is HIV positive, given that I saw an HIV test record a positive test result. And that's not 100% because these tests are never 100%, right? So we'll kind of walk through this and then we'll work through that example, put some actual numbers to it. But we know starting out that a conditional probability, which is what we were interested in, state of nature given the outcome of the test, is the intersection of two events divided by the probability of what we're conditioning on. You know, we've already looked at this with events A and B, just now we're calling this S1E, state of nature, and the outcome of this experiment or the outcome of this test. Okay. Now the problem is, if I think about here, my state of nature was that they actually have the disease, and my outcome of the test was E. Well, the problem is, do I just know if somebody takes an HIV test, probability it comes back positive? Well, no, that probability depends on whether or not they have the disease, right? So I'm never going to just know the probability that the test comes back positive. I only know the probability that it comes back positive if the person actually has it, right? These companies put out what their false positive, what their false negative, and what their kind of true positive, true negative results are. So I can break these down a little bit further, okay? So first of all, I know that I can rewrite this intersection of these two events as a conditional probability times whatever I'm conditioning on. Okay. So, and actually, why do I feel like this isn't right? Here we go. I was going to say, that shouldn't be right. So this is just kind of rearranging my multiplication rule. So if I want the intersection of two events, excuse me, I can rewrite this as the conditional probability of those events times whatever I'm conditioning on. That was just taking that multiplication rule and kind of rearranging. So I can plug that in for my numerator. And then the denominator is a little bit trickier. All right, if I take the two states of nature and their intersections with this specific outcome of the test, and I add those up, that should just be the probability that I get a positive test result. Right? You kind of think about maybe why. So what would this represent? this, if we think about not probabilities, so you know how we were just taking frequencies and converting them into probabilities? I can work the other way as well. I can start out with a probability, you tell me the number of counties in the data set, well, I can just multiply that by that probability to get the number of counties that were in that group. So in the case of like this HIV example, I can take everybody who, instead of thinking about these as probabilities, thinking about them as frequencies might help. Everybody who has HIV and gets a positive test result, plus everybody who doesn't have HIV and gets a positive test result. So these would be the true positives plus the false positives. If I add those up, that's just everybody who gets a positive test result. Same kind of idea, if I turn those frequencies into probabilities, the probability of those two groups added together is the probability of that outcome of the test and get them interested. Okay. So I'm just taking everybody who had HIV and got a positive test result, adding to that, everybody that had HIV and got, everybody that doesn't have HIV and also got a positive test result. Okay. Well, that's what's in my denominator. So I can just go ahead and plug that in. So I can rewrite my intersection once again as conditional times non-conditioning on. Rewrite this as a conditional times non-conditioning on. I now have the probability of E written out in terms of conditional probabilities. And I have that numerator, the intersection, which I can write out as kind of this, using this multiplication rule, right? The conditional probability times whatever I'm conditioning on. So the reason why this works, right? And once again, let's think about what these probabilities, the groups they would represent, and I'll probably talk about it in terms of frequency. So here, this is, what's the probability someone gets a positive test result, given they have the disease, right? They're in state of nature 1. Times the probability that they actually have the disease. So basically, it's like, if I were to have a room full of people and I'm all knowing, I know whether or not they have the disease, and then I run a test for every person, I see their outcome. I would take everybody in the room, and then I would only take the people that have the disease. So the probability they have the disease, that could be turned into a frequency. Now that I have those people that have the disease, well, how many of them will get a positive test result? Well, whatever that kind of true positive result is for that specific brand or company that's doing the test. So my numerator is going to represent everybody who has the disease and gets a positive test result. I'm then going to divide that by, remember, what did this denominator represent originally? Well, that was just everybody who got a positive test result. So I'm taking the number of people who have the disease and get a positive test result and dividing that by just the total number of people who get a positive test result, which would also include this false positive group, right? The people who are in the other state of nature. So kind of see how this plays out. We can get some really crazy, I guess, non-intuitive results here, right? So I color coded these so we can kind of line up where I was kind of substituting things in. Remind me, I'll come back to this slide on Monday, but I want to try to work through this example before I leave, okay? So I can start out kind of with this probability that someone has HIV. So I would select someone at random, very small percent of our population, right? So it's around 0.5%. I then want to say, okay, given that this person actually has HIV, these tests are pretty good at reporting a positive test result, right? They're 99.9% accurate. Okay. Well, if the probability someone has HIV is 0.006, what's the probability that someone doesn't have HIV? You either have the disease or you don't. So what should these two states of nature's probabilities add up to? 1. So 0.994, right? And then kind of we look at the company that does this test and they said, well, look, given that someone doesn't have HIV, if they were to take our test, our false positive rate, right? Those people that don't have the disease, it's actually relatively high, right? It's actually 1%. Now I say relatively high. 1% isn't a high number, but I mean, taking an HIV test and it tells you have HIV, that one person is going to care, right? So 1%, right, is still relatively high. Okay. So what's going to end up happening is there's a really small number of people that have the disease. Now we'll be able to accurately identify all of them that have it almost, right? The test is very accurate. So let's say we were to give an HIV test to every single person in the US, right? There's going to be a small number of people who have the disease, but we're going to identify almost all of them, right? But you know, if I take 0.5% of the population, it's roughly what, 1.5 million people, and I'm almost identifying all of them accurately, I can kind of think about it as the people who actually have the disease and get a positive test result, right, would be about 1.5 million. So everybody who gets a positive test result and actually has the disease would be about 1.5 million. So they're going to be one type of person I could see get a positive test result. What are the other people I could see get a positive test result? Well, most people don't have HIV, right? So roughly 300 million, we'll just call it, right? In the US, we'll call that the kind of the population. I know it's a little bit higher, but just to have a nice, easy number to think about. So we've got about 300 million people that don't have HIV, but if we give all of them a test, well, 1% of the time, if you don't have the disease, you get a positive test result. So of these 300 million people, how many people are we going to see get a positive test result? About 3 million, right? 1% of the population of 300 million. So notice that if we were to give everybody an HIV test, the number of people that get a positive result and don't have the disease is actually twice as large as the number of people who are going to see a positive test result and have the disease. And this is just by sheer fact that most people don't have it, right? So even if our tests are like producing small percentages of false positives, that's still a lot of people, right? So if we work this out, we're going to use these probabilities, right? And we go back here. Oops, how far back do I have to go? There we go. Well, I can find these probabilities. What's the probability that someone has HIV? I got that. What's the probability that they have HIV, they get a positive test result? I've got that. Now notice, this is the exact same thing as the first part of the denominator, because this is really just representing the people who have the disease and get a positive test result. Now the other group that I have here is, well, what's the probability they don't have HIV? And then given that they don't have HIV, what's the probability to get a positive test result? So I have all these probabilities, okay? So I'll go ahead, like I said, we'll come back to that slide next week. I'll also show you another way of thinking about this. You kind of write out a probability tree. I'll work this into one of the examples that we work through next week. But for now, I just want to kind of show you the counterintuitive result, right? So I've got all my probabilities. We wrote those up on the board. We're okay with that. Okay. We know that what we want to find is the probability that if we see a positive test result, right? Given that we see a positive test result, what's the probability that person actually has the disease, right? If we were just to administer this test to someone at random. So I write out my base formula. I can go back to where I had S1, S2, and E. And we only had one example to this point, so we were thinking of S1 as having the disease, S2 is not. I'm just going to write this out in the context of my example, right? What my states of nature are and what my test results were. So here I was just writing POS, which good abbreviation there. So I was writing that to just be like a positive test result. When I do this on the board, generally I'll write like the outcome of the test is positive, right? So test is equal to positive, right? So I can just fill everything in. I've got those values. I kind of already mentioned, we can just plug those in. And the real counterintuitive result is if I just administer a test at random to somebody, because most people don't have the disease and the false positive rate is like somewhat high, I actually get that probably the person that actually has HIV is only about 40%, right? Or 38%. So it's kind of an introduction to Bayes' theorem. Hopefully we kind of see like, oh, we get some pretty counterintuitive results. This might be an interesting thing to take different examples. I'll give you some other ones on Monday. We'll talk a little bit more about some of the things that might make some of these problems a little bit easier. But you will see that next Excel assignment pop up on Canvas. I would suggest, don't put it off too far down. The due date will be in a couple of weeks, but really the bulk of that assignment will be what we did today. So as long as it's fresh, start working on it. Okay. All right. Oh, one more thing before you guys leave. So